Welcome back to the video course on fluid mechanics. So, we were discussing about the dynamics of fluid flow. We have seen the derivation of the Euler's equation, and from the Euler's equation how to derive the Bernoulli's equation, that also we have seen in the last lecture. So, today we will further see the applications of Bernoulli's equations and then many other practical cases where this equation can be utilized effectively, that we will discuss today. So, as we have seen for Bernoulli's equation, as you can see in this slide, as per the Bernoulli's equation, which can also be derived from the conservation of energy, we have seen the energy per unit weight plus the pressure energy plus unit weight plus kinetic energy per unit weight plus potential energy per unit weight is equal to total energy per unit weight of the system. So, we have already seen that the total energy in the system does not change as per the conservation of energy. So, that we can say that total head does not change. So, that is this way also we can derive the Bernoulli's equation, and also we have seen this between 2 points. If you take total head at 1 is equal to total head at 2, if you consider 2 section in a pipe flow. So, so we have this principle we can utilize in many forms, including the considering the total energy of the system, including the work done per unit weight or the energy supplied per unit weight, as you can see in this slide. So, this Bernoulli's equation is applicable to many problems, but if the flow is irrotational, we can also say along a streamline, but if the flow is irrotational, we can also use this across the streamline, and some of the restrictions we will discuss later. So, first we will see the some of the important applications of the Bernoulli's equation. So, let us consider say streamline around a blunt body like in this slide. So, here you can see that the flow is coming in this direction, and due to the blunt body effect there will be a stagnation point like this. So, we can find out this, case 1 here, the application of the Bernoulli's equation, case 1 is stagnation pressure. So, we can isolate a point in the field where velocity is 0, that is so called stagnation point. So, here in this particular case, in this figure, this point 2 will be the stagnation point. And now here, by considering the flow here at this location here at section 1 and section 2, between these two sections, if we apply the Bernoulli's equation along a streamline from 1 to 2, we can write, so since here this say if you consider the datum like this horizontal, so that the flow is horizontal. So, Z1 is equal to Z2. So, applying the Bernoulli's equation along the streamline between section 1 and 2, we can write P1 by rho g plus U1 square by 2g plus Z1 is equal to P2 by rho g plus U2 square by 2g plus Z2. So, here P1 is the pressure at section 1, P2 is the pressure at section 2, and U1 is the velocity at section 1, U2 is the velocity at section 2, and rho is the density of the liquid, and g is the acceleration due to gravity. So, here we can see that we are now considering the stagnation point. So, due to the stagnation point, the velocity at that point will be 0. So, that this equation we can write P1 by rho, if you multiply both sides by g. So, P1 by rho plus U1 square by 2 is equal to P2 by rho. So, since Z1 is equal to Z2, this is cancelled, and U2, since we are considering stagnation point, we can write U2 is equal to 0. So, that P1 by rho plus U1 square by 2 is equal to P2 by rho. So, from this we can write P2 is equal to P1 plus half rho U1 square. So, by considering the point 2, we can find out the pressure at the stagnation point. So, that is so called stagnation pressure. So, now we have applied the Bernoulli's equation between 2 points. One is the stagnation point and other one is the particular section 1 so that we could find the stagnation pressure. So, this is one of the basic application of the Bernoulli's equation in fluid mechanics. And then there are a number of other applications. So, based upon the stagnation pressure itself, let us consider a pitot tube. So, pitot tube is generally used to measure the mean flow velocity, especially in pipes, in closed conduits such as pipes. So, here you can see in this slide a pipe is there, the flow direction is like this, and then we can say we want to find the pressure at the central line. So here say if you want to find the pressure say at this point, say at this particular, that means central line velocity. So what we can do is we can just consider, we can immerse, we can put the pitot tube like this at this particular point to where we want to find the velocity. So and then we should have another point also where we can introduce a piezometric tube like this. So this is the piezometric tube here at section 1 and at section 2 we introduce the pitot tube. So the fluid levels, you can see that there will be a difference, since this is mainly due to the velocity effect at the center line. So the head at due to the at piezometric level will be H1 from the center line, and on the pitot tube it will be S2 from the center line. So now if you apply the Bernoulli's equation between section this section 1 and section 2, we can write this P2. So now say here you can see that at section 1 the pressure is P1. So P1 plus half rho U1 square will be the total head at section 1 and section 2 it will be P2 is equal to P1 plus half rho U1 square. So that P2 can be written as rho G S2. So from which we can get the velocity at the central line. So for the pipe flow, so that is equal to U is equal to square root of 2G S2 minus H1. So this is the way which we by introducing a piezometer and then a pitot tube, we can find the mean flow velocity of flow like in a pipe like shown in this figure. So we have found the velocity at the central line velocity by considering 2 points 1 and 2, and at point 1 we introduced a piezometer, and at point 2 we introduced a pitot tube, and then we are trying to find the central line velocity. So we can get the Bernoulli's, we can use the Bernoulli's equation between section 1 and 2 as in this figure, and finally U is equal to square root of 2G S2 minus H1, whereas H2 minus H1 is the head level between this piezometer at section 1 and the pitot tube introduced at section 2. So the earlier case actually say we should have so the case which we just discussed, now here we should have one piezometer and as well as a pitot tube to find out the mean velocity of flow. But instead of this arrangement, we can have another type of arrangement to find the mean velocity of flow, a pitostatic tube like in this figure. So here you can see that a pitostatic tube is introduced here. So say with respect to the pipe where the pressure, the velocity is found. So this in this mechanism it combines the tubes and the connected to a manometer, the pitot tube. So here a manometer is shown here, and the central line velocity where we are trying to measure the velocity, this manometer tube is introduced at this location, and then there is an opening with respect to this tube here at section 1, and then you can see that when the manometer is connected, where the fluid level difference will be like this at A and at B as shown in this slide. So P2, the pressure at the central line P2 is static, so we can write P2 is equal to P1 plus half rho U1 square with respect to this section 1 as we have seen earlier. And then if you consider the manometer here, so this PA is equal to the pressure, the pressure at A, PA is equal to P2 plus rho G X. This fluid level, this rho G is the unit weight or the specific weight of the liquid, and this X is this difference between this level as shown in here, this line and this line. So that is X. So PA is equal to P2 plus rho G X, and PB is equal to the pressure at section B here at particular location B, PB is equal to P1 plus P1 is the with respect to the fluid pressure at this section 1 P1 plus rho G x minus H. So, this difference rho G into x minus H plus the density of the manometer liquid into G into H. So, this is H. So, rho G into H. So, from which since with respect to the conditions P A is equal to P B. So, we can equate this both equations. So, that P2 plus rho G x is equal to P1 plus rho G into x minus H plus rho manometer into GH, manometer liquid density into GH. So, now if we use this relationship here in the previous equation, we can write P1 plus rho Hg into rho manometer minus rho is equal to P1 plus rho U1 square by 2. So, now with respect to this we can find P2 with respect to this equation, and then we can substitute that here. So, that will give U1 the velocity, so for the center line velocity as square root of 2 GH rho the density of the manometer liquid minus the density in the pipe divided by rho. So, U1 is equal to square root of 2 GH into rho m minus rho divided by rho. So, like this here a pitot-static tube is used to measure the mean velocity of flow in a pipe, instead of as we have seen in the previous case here we had to use a piezometer as well as a pitot tube, but here the mechanism is pitot-static tube, and then we can find the velocity as shown here. So, now the third case which we will be discussing here is the application of Bernoulli's equation for a Venturimeter. So, you can see that this Venturimeter is used to find the discharge in a pipe, and this is the pipe which we want to find the discharge, and for this Venturimeter arrangement there will be a converging section, as you can see here there will be a converging section, and then there will be a diverging section like this. So, the converging section and diverging section, and then at this particular point you can see a minimum cross sectional area, and then we will be using here a manometer like this, and which will be connected between this particular section before the divergence start, this particular section 1 and then particular section 2 as shown in this figure, and then with the manometer liquid level you can see the fluid levels at a height difference of h. So, now with respect to this converging section, diverging section, now we want to find the discharge, and then that is the pressure difference which we measure between discharge is obtained from the pressure difference measurement between section 1 and 2. So, now if you apply the Bernoulli's equation along the streamline from point 1 to 2 in the previous figure from this point 1 to point 2, then we can write P1 by rho G plus U1 square by 2G plus Z1 is equal to P2 by rho G plus U2 square by 2G plus Z2, where P1 and P2 are the pressure at section 1 and 2, U1 and U2 are the velocities at section 1 and 2, and Z1 and Z2 are the height difference with respect to the datum. Here this is Z1 and Z2. So, now from the continuity equation you can write Q is equal to A1 U1 is equal to A2 U2. With respect to the velocity and area of cross section we can write Q, the discharge is same. So, Q is equal to A1 U1 is equal to A2 U2, from which we can write U2 is equal to U1 A1 by A2. So, now we will substitute for U2 in this equation, so that we can write P1 minus P2 by rho G plus Z1 minus Z2 is equal to U1 square by 2G into A1 by A2 all square minus 1. So, from which we can find the velocity, the center line velocity, that means at this location we can find the velocity for the by using the Venturimeter. So, once the velocity is known we can just multiply it by Q is equal to A1 U1, that gives the discharge through the pipe. So, this is another mechanism which we generally use to either to find the velocity or say to find the discharge depending upon the case for in a pipe flow. So, this is another application is called Venturimeter. So, then as far as this kinds of hydraulic equipments are concerned, so Venturimeter is concerned, we can see that the theoretical discharge is Q ideal discharge is equal to U1 A1, but actual discharge you can see that there will be a reduction with respect to this measurement. So the actual discharge will not be equal to theoretical discharge. So actual discharge, to obtain the actual discharge Q actual, we have to multiply by a coefficient of discharge CD, so that Q actually is equal to CD by CD into Q theoretical. So that we can write Q actual discharge is equal to CD into U1 into A1. So we can write with respect to the previous equation which we derived for U1, the Q actual is equal to the coefficient of discharge multiplied by A1 into A2. So A1 is the cross section at section 1 and A2 is the cross section at the converging cone. A2 multiplied by square root of 2g into P1 minus P2 by rho g plus Z1 minus Z2 by A1 square minus A2 square. So this is the actual discharge. So there is, with respect to this kinds of measurement, there is a difference between the actual discharge and theoretical discharge. So we have to multiply by the coefficient of discharge. So Q actual is equal to Q theoretical into coefficient of discharge. So now say we can, with respect to the, in terms of the manometer readings, we can write P1 plus rho g Z1 is equal to P2 plus the density of manometer liquid into GH plus rho g into Z2 minus H. So that this we can write P1 minus P2 by rho g plus Z1 minus Z2 is equal to H into rho manometer by rho minus 1. So actual discharge that can be written as CD into A1 into A2 square root of 2GH rho manometer by rho, the density of the fluid in the pipe minus 1 divided by A1 square minus A2 square. So so like this, by using a Venturimeter we can use we can measure the velocity or the discharge in a pipe flow. So now the application as far as Venturimeter is concerned, now we will see further application of Bernoulli equation. So as we have seen for the Venturimeter, we can also have other mechanism for flow measurements, the discharge or velocity, like say the various flow measurement equipments are shown here, just like orifice as shown in this figure, and then nozzles are shown here, and Venturimeter which we have already discussed. So these are some of the equipments used for flow measurements, which we utilize the Bernoulli equations and the Bernoulli equation and the continuity equation together, so that we can find the flow velocity or the discharge at particular sections of a pipeline. Especially this mechanism is used for pipeline. This is one of the application of the Bernoulli equation. Now we will go to further applications of the Bernoulli equation. So fourth one is flow through orifice. So you can see that this orifice is a mechanism. Say if there is a tank like in this slide, and then if there is a small hole like this, and so water will be coming from the tank as in the case of a jet. So this is so called an orifice. There are different forms of orifice. So this is one of the simple most form of the orifice. So this also we can utilize to find the time to find empty a tank, or to the particular discharge measurement. This can be utilized. So here for the flow through orifice, say here you can see that say whenever the fluid is coming out of the orifice, so this is a small hole which is so called orifice, then all the streamlines are converging to the opening here at the orifice, and then you can see that there is a location where the streamlines are converging, and the area cross section of the jet is the minimum. So this section is so called vena contractor. So vena contractor is the where streamlines contract after orifice to minimum and then become parallel like this. You can see that now the streamlines become parallel. So at this particular location, also called a vena contractor, there will be a velocity and pressure. The velocity and pressure will be uniform across this particular location of the vena contractor. So this is so called orifice. As we can see that this is also the orifice, as I mentioned, can be utilized for the velocity or the discharge measurement. So the same principle is utilized there also. So here now we are considering the vena contracta, and now between say the tank which we are considering here, if we consider the surface of the tank at this particular location 0.1, and then if we consider the orifice location or the particular vena contracta which we are considering at section 2. So we are considering now two position 1 and position 2. Now between position 1 and 2, you can see that now this jet is going freely to the atmosphere. So the pressure at this location will be 0, and this is an open surface. So at location 1 the pressure will be 0. So P1 is equal to 0, P2 is equal to 0, and this is open open surface of the tank. So there the velocity U1 is equal to 0, and then you can see that the datum head Z1, if you consider this center of the orifice as the datum, then Z1 is equal to H and Z2 is equal to 0, and then if we can apply the Bernoulli's equation between section 1 and 2. So between this section, position points 1 and 2, we can see that we will get H is equal to U2 square by 2G, or we can write U2 is equal to square root of 2GH. So the velocity at this location U2 at location 2 will be U2, that is equal to square root of 2GH. So now, as we have seen earlier, as far as the coefficient of discharge, here again the velocity, the actual velocity will be different from the theoretical velocity. So we have to multiply by a factor called coefficient of velocity for this kinds of problems. So due to the friction, the actual velocity will be different. So when the fluid is coming out of the orifice, there will be friction with respect to the atmosphere, and then due to the frictional effect, the actual velocity will be slightly different. So we have to multiply it by a coefficient of so called velocity. So the actual velocity is equal to coefficient of velocity into the theoretical velocity. So this coefficient of velocity for these kinds of problems, it is varies from 0.97 to 0.99 depending upon the various conditions like orifice locations or orifice diameter and other conditions. So the actual velocity is obtained as the coefficient of velocity multiplied by the theoretical velocity. So this is the flow through orifice, and finally also for the orifice you can see that if you consider the vena contracta here, then with respect to the vena contracta, the actual area of the jet is the area of vena contracta. So the jet which we are considering out of the orifice, the actual area cross section of the jet is area of the vena contracta. So A actual is equal to, we have to multiply again by a coefficient of contraction into the area of the area cross section of the orifice. So actual area is equal to coefficient of contraction multiplied by the cross sectional area of the orifice. So finally, now if you want to find the actual discharge, Q actual is equal to area of cross section into U. So Q actual is equal to A actual, that means A actual is into A orifice into U theoretical. So finally Q actually is equal to coefficient of discharge into area of cross section of the orifice into the theoretical velocity. So this gives the actual discharge from the orifice. So this has got many practical applications, as I mentioned. Even for flow measurement, orifice can be used. So many other applications are there in fluid mechanics for this flow through orifice. So we are now using the three coefficients. One is the coefficient of contraction when to find the actual area, and second one is the coefficient of velocity to find the actual velocity, and the actual discharge. Finally we are getting CD is equal to CC into CV. That means coefficient of discharge is equal to coefficient of contraction multiplied by the coefficient of velocity. So that is CD. So finally we get the actual discharge. So this is say another application of the Bernoulli's equation. Now just to find the time for emptying a tank, as I mentioned, this Bernoulli's equation again can be utilized. So if you want to find how much time is taken say for a liquid, say in a tank, for the liquid in a tank, say to come from level H1 to S2. So if you want to find, so again Bernoulli's equation can be utilized here, and then say if H is the level difference between H1 minus S2 is H, so that we can write the discharge Q is equal to A into the velocity. So that is, since the level is going down, we are using minus here, so this is equal to minus A into del H by del T. So with respect to time, this head is changing, so Q is equal to minus A into del H by del T. So this we want to find here the time for emptying tank from H1 to H2. So from this equation we can write delta T is equal to minus A into, now we will write the discharge equation which we have seen earlier. So delta T is equal to minus A divided by CD into A0 into root 2G into delta H by root H. So now you can integrate this expression with respect to the levels H1 to S2. So that T is equal to minus A into CD into A0 into root 2G into integral H1 to S2 del H by square root of H. So that if we integrate this expression, we will get the finally the time for emptying a tank H1 to S2 will be equal to minus 2A divided by CD into A0 root 2G into square root of S2 minus square root of H1. So here again we have used the Bernoulli's equation to find the time for emptying a tank from one level to another level. So like this, the various applications are there. And now earlier we have seen just an orifice which is directly emptying the liquid to or the water to the atmosphere. So now if we are considering a submerged orifice as shown in this figure, so here you can see there is an orifice here at location 2, and then this through this orifice the liquid is passing from tank 1 to tank 2, very adjacent tanks. So they finally after some time this become a submerged orifice. So to find the discharge passing the submerged or the velocity of flow through the submerged orifice, we can apply the Bernoulli's equation from this point 1 to this point 2 at this end of the orifice. So we can write from Bernoulli's equation, we can write P1 by rho g plus U1 square by 2g plus Z1 is equal to P2 by rho g plus U2 square by 2g plus Z2. So here you can see that since due to the atmospheric pressure, P1 by rho g will be equal to 0, and here the velocity will be 0, so U1 square by 2g also 0, and here Z1 is equal to this H1 if you take the datum as the center line of the orifice. So H1 is Z1, and then P2 by rho g is we can write as rho g S2 by rho g plus U2 square. So here the velocity is U2, so U2 square by 2g. So since the datum is taken, Z2 is equal to 0. Finally we can get this velocity of flow U2 is equal to square root of 2g into H1 minus H2. So H1 minus H2 is actually the level difference between this level and this level. So this gives the H1 minus H2. So the velocity is found, and then we can find the discharge of Q is equal to, we can use the continuity equation, Q is equal to area cross section area of the orifice into velocity, and finally the actual discharge is equal, we have to multiply by the coefficient of discharge area cross section of the orifice into the velocity which we have calculated here. So this is the case of a submerged orifice. Now we will see another case here, so called a confined flow. So if we consider which is a confined with respect to this tank as shown here. So the liquid is coming, flow is coming in this direction, and then flow is going through another say nozzle at location 2 here. So if you want to find for this confined flow the discharge or any other parameter or the velocity of flow at section 2, again we can use the Bernoulli's equation as shown between the section 1 here and section 2. So when we apply the Bernoulli's equation, we can write P1 plus half rho V1 square plus gamma Z1 is equal to P2 plus half rho V2 square plus gamma Z2. So here you can see this is open to atmosphere here, so P1 is equal to, and here also open to this, so P1 equal to P2 is equal to 0, and Z1 is equal to H, and Z2 we are taking this as the datum, so Z2 is equal to 0. Finally, we get half V1 square plus GH is equal to half V2 square, and then we can find the velocity, and from that we can get the discharge. So this is as far as if we consider confined flow as shown in this figure. And now there are many other applications for Bernoulli's equation. So some of the open channel flow types problem again we will discuss here. Next one is sluice gate. So if you want to find the discharge passing through a sluice gate, so here you can see this figure here. So in this figure, so you know that a sluice gate is generally in a reservoir or say different chemical plants or water supply plants. We just use this gate to pass particular amount of discharge, and if you want to find how much is the discharge passing through this particular opening, again we can use the Bernoulli's and continuity equation for a sluice gate. So sluice gate is here, and the liquid level is at this level, and the flow is this coming in this direction, and here. And after the gate, again as we have seen here, again a vena contracta will be formed, that means minimum cross sectional area where the streamlines will be parallel, and then we will be applying the Bernoulli's equation between the section 1 and section 2 of this, where the area of cross section is minimum here between section 1 and 2. So here applying the Bernoulli's equation and continuity equation. So if you apply the continuity equation between section 1 and 2, we can write Q is equal to A1 B1 is equal to this, if B is the width of this opening or with respect to this location here. So B into B1 Z1, that is equal to A2 V2, that is B V2 Z2. So now where B is the say the thickness or the width which you are considering. So now we can apply the Bernoulli's equation between point 1 and point 2, so that we can write P1 plus half rho V1 square plus gamma Z1 is equal to P2 plus half rho V2 square plus gamma Z2. So now say here P1 and P2, here you can see that it is atmospheric pressure. So P1 P2 we don't have to consider. So from this equation we can find out the velocity, say for example V2, and then we can get an expression for the discharge passing through the gate as Q is equal to Z2B into square root of 2G into Z1 minus Z2 divided by 1 minus Z2 by Z1's whole square. So this way, so here this is Z1 here, this is the bottom of the sluice gate is considered as the datum, and this is Z1 here, and Z2 is this depth of at this particular location at section 2 and Z1 is the depth at section 1. So this way, for here also P1 equal to P2 equal to 0, and then by using the Bernoulli's equation and continuity equation we can find the discharge passing through the sluice gate. So this is one of the application of, say, as far as open channel flow is concerned. And then another applications is application for the Bernoulli's equation for weir or notch. So here you can see that, say weir is here, so we want to find how much is the discharge passing over the weir or a notch. So this here, this is rectangular sharp crested weir. So if you want to find, we can say here again in this particular figure, we will be considering this location a streamline like this, and then between section 1 and 2 we will be considering, so this is 2 and this is 1, between section 1 and 2 we will be considering the Bernoulli's equation. So P1, if you consider this particular point, P1 is equal to this height of the depth of flow with respect to this point 1, P1 is equal to gamma H, and then here it is atmospheric pressure, so we can neglect the pressure, so P2 is equal to 0. So if you consider between section 1 and 2, if you apply the Bernoulli's equation, we can show that Q is equal to C1 into H into B root 2 GH, or this is equal to C1 into B into square root of 2G into h to the power 3 by 2. So, where C1 is a constant as far as this wear or notch is concerned. So, like this we can apply this Bernoulli's equation in combination with the continuity equation to large varieties of problem in practical cases. So, again here if you consider a general equation for the wear or notch, the general equation here you can see this is the sharp crested wear, and then we will consider a small strip of elemental strip through a notch, and then you can see that this velocity u is equal to square root of 2 gh, and discharge through the strip delta q is equal to area of cross section into velocity. So, b delta h into square root of 2 gh with respect to this figure here, and then we can just integrate between 0 to h. If this is h is the depth of flow with respect to the crust or the wear as shown in this figure. So, this is the depth of flow. So, we can integrate between from 0 to h. So, that q theoretical the theoretical discharge is square root of 2 g integral 0 to h b h to the power half dh, and then we can integrate here the theoretical discharge is equal to b root 2 g square root integral 0 to h square root of h dh, that is equal to 2 by 3 b root 2 g h to the power 3 by 2, and the actual discharge as we have seen here, again we have to use a coefficient of discharge. So, q actually is equal to c d into 3 by 2 b root 2 g h to the power 3 by 2. So, this is another application of the Bernoulli's equation in combination with the continuity equation. So, similarly if you consider a V notch as shown in this figure. So, again we can just this V notch is this is just a triangular V here. So, here this B, the width at particular location B can be found at depth h from the surface of the water, the total depth is h. So, B is equal to 2 times h minus h into tan theta by 2, where theta is the angle of the V notch. Then q theoretically is equal to 2 into root 2 g tan theta by 2 integral 0 to h minus h into square root of small h dh. So, that will give finally the equation as this is equal to 8 by 15 root 2 g tan theta by 2 h to the power 5 by 2. So, the in a triangular wear or a V notch, the discharge will be varying with respect to h to the power the total depth of flow h to the power 5 by 2, and actual discharge is equal to the coefficient of discharge multiplied by the theoretical discharge as shown in this slide. So, like this by using the Bernoulli's equation and the continuity equation, we can solve many practical problems in hydraulics or including the closed conduit flow like pipe flow, and also open channel flow as we have seen the notches, then wears or the sluice gate problem. So, different kinds of problems we can solve using the simplified form of the Bernoulli's equation and the continuity equation. You can see all this problem, it is very simple approach. Bernoulli's equation is a simple equation, so that we can easily without much complexities we can easily approximate the what kind of flow is coming, and then we can apply the Bernoulli's equation between two sections, between 2 points on a streamline, and then we can find either the discharge or the velocity or the pressure what we are looking for between the two sections. So, these are the applications, some of the important applications of the Bernoulli's equations. So, before going further, say with the derivation of other fundamentals and momentum equations, we will just see some aspect of the energy, the total energy, and then with respect to this the hydraulic grade line and the energy line. So, say we have already seen with respect to the Bernoulli's equation, total head is equal to the pressure head plus velocity head plus datum head. So, this the total energy will be, of course there will be losses also, or the internal force will be also, internal energy will be also there. So, that also we have to consider, and that is total energy. But while finding this energy at various section of a pipeline or an open channel flow, depending upon the case which we are doing in the problem. So, we can represent two lines called energy line and hydraulic grade line. So, this energy line and hydraulic grade line are the graphical forms of actually actually the Bernoulli's equation. So energy line and hydraulic gradient line are actually the graphical forms of the Bernoulli's equation. So the basic principle as we have seen is sum of the various energies of fluid remains constant as the fluid moves from one section to another, or the energy is conserved. So when we consider a pipe flow like this, so if you consider this as a pipe, then between one section to another section we can see that the fluid, the various energies remains constant as the fluid move from one section to another section. And now since our the equation which we derived, Bernoulli's equation is say we are derived for steady inviscid incompressible flow, so that total energy remains constant along a streamline. So this is the basic equation. So the energy line concept and hydraulic gradient line concept is also based upon this say the conservation of energy. That means the total energy remains constant along a streamline. So if you consider the Bernoulli's equation, the pressure head P by gamma plus velocity head plus V square by 2g plus Z the datum head, that is equal to constant on a streamline. So that we can write this is equal to H. So this is pressure head plus velocity head plus datum head is equal to total head H as shown in this slide here. So now say if we consider this figure is say taken from this Munson et al. Fundamentals of fluid mechanics, which is slightly modified here. You can see here, say if you consider a pipe flow like this, now say if you take the piezometer level at this location and at 1 and at location 2. So here you can see that piezometer is concerned, it indicates the pressure head and datum head. So with respect to piezometer we can write P by gamma plus Z, that is the piezometric head. So this is actually static pressure, does not measure the velocity head. So this gives the piezometric head here at section 1 and here the at section 2 P2 by gamma plus Z2. So that is the piezometric head. So the hydraulic gradient line is actually the locus of a series of piezometric taps. So here at different locations, so if we consider this as a pipe at different locations, if you just find the piezometric head, so that is actually the velocity head plus the datum head. So so if you just draw the locus of a series of piezometric taps, if you have a long pipeline as can here you can see this is a very long pipeline which we are considering. So with respect to this is the datum. So now with reference to this pipeline you can have a series of say piezometer, and then we can see that the piezometric we can plot the piezometric heads, and then you can, if you just put the locus of this piezometric head, that gives the hydraulic gradient line. So this gives this. So this is the fluid flow, this is pipe flow. So here this is the datum which we are considering. So here this is Z3, if you can measure to the central line, this is Z2 to the central line, this is Z1 to the central line. So when we plot the locus of the piezometric heads, that gives the hydraulic gradient line. So this hydraulic gradient line doesn't include the velocity head. So here we are not considering the velocity head at this locations, various locations which we have seen. So that gives the hydraulic gradient line. So hydraulic gradient line is the locus of a series of piezometric taps. Now if you, so now the pipe which we are, say for example, now we consider a pipe flow like this, and we have 3 sections, section 1 section 2 section 3 as shown in this figure. Now if you can introduce piezometer like here, you can introduce the piezometer at the central line as we have seen earlier. So if a piezometer is introduced here, so here with respect to this piezometer you can see that it will be considering the velocity head also. So for this 3 section, if you plot the if you find the piezometric levels, so you can see that it is varying like this. So with respect to this, if you just plot the the say the locus of the where the pitot tubes levels. So here this is the level, this is the level, this is the level. So this lines gives the energy line. So now the energy line is say you can see that now energy lines include the datum head, the pressure head and the velocity head. So where say at various locations, if you can say pipeline, various locations, if you introduce the pitot tubes and then if you just get the levels of the pitot tubes and then if you join those levels with a line, so that line is called the energy line. So as shown here, so with reference to the hydraulic graded line, the difference is that there is extra the velocity head. So for hydraulic graded line we consider only the datum head and the pressure head. We are using which is the locus of the levels with reference to piezometric tubes at various locations. But the energy line is concerned, we are considering the velocity head also. So you can see in this figure we are introducing the pitot tubes at various locations and then we can finally get a line so called the energy line. So this hydraulic graded line and energy line concepts are very useful, especially for pipe flow analysis and open joint flow analysis. So this gives say this is coming here again we are using the Bernoulli's equation or the total energy principle, so that we are the conservation of energy is used, the principle of conservation of energy is used. So this concept of energy line and hydraulic graded line is used in many problems, especially pipeline problems, also sometimes in fluid, the open joint flow also we utilize this energy line concept and hydraulic graded line concept. So in all these problems what we have seen so far, when we measure the velocity, we are getting the mean velocity, or say the velocity measurement is say with respect to most of this one dimensional problem, v is the average or the mean velocity. So here another say we have to do a correction with respect to this since we are considering the mean flow. So if you consider a pipe, if this is considered as a pipe, then you can see that with reference to this, say here say we are considering the mean flow velocity. So with respect to the mean flow velocity, the average velocity at a cross section is taken. So the actual velocity may not be uniform. So the concept which we are using here is that the velocity is, the mean velocity is taken such a way that and then it is multiplied by all other say area of cross section etc. So Q is equal to area of cross section into velocity. So this V is the mean velocity. So this mean velocity is not actually, if you consider a pipe flow like this with reference to the center line. So the mean velocity, you can see that the pressure, the velocity is varying like this. So it will be maximum at the center line and then it will be minimum 0 at both sides of the pipe wall, it will be 0. So the mean velocity concept is actually will not give a correct value as far as when we find the various measurement like a discharge. So it will not give the correct value, we have to use a correction factor. So as far as kinetic energy is concerned, we have to, the actual velocity is non-uniform, as you can see in this pipe flow or even the open joint flow also, what we are considering will be non-uniform flow. So for the non-uniform flow we have to use a correction factor called kinetic energy correction factor, which is so called alpha. So this alpha we can obtain, say we can take say with respect to the mean velocity what is the discharge, or with respect to the continuity equation we can derive this alpha is equal to integral v cube dA divided by capital V cube A, where small v is the varying velocity. So here you can see that the velocity is varying. So various section you can consider like this, and then it is the integral of v cube. V is the velocity at any point, and then capital V is the mean flow velocity. So the alpha, the energy correction factor alpha is equal to integral small v cube dA divided by capital V cube area of cross section of the pipe or the channel section which you are considering. So, the alpha is equal to integral V cube dA by capital V cube A, where capital V is the mean flow velocity, A is the area of cross section, and small v is the velocity varying from various sections which you are considering. So, this kinetic, or whenever we consider the V square by 2g term, we have to use this, we have to multiply by the kinetic energy correction factor alpha, so that we get a correct velocity head or the correct kinetic energy. So, alpha, if you consider the flow to be uniform, then you can say that alpha is equal to 1, so that no need of this correction, and if it is greater than 1, we can say that so say it will be greater than 1 for all other forms, that means non-uniform flow conditions it will be greater than 1, and then for laminar flow in pipes this will be equal to 2, we can derive as equal to 2. And finally, if you use this energy, the energy kinetic energy correction factor, finally the energy equation becomes P1 by gamma plus alpha V1 square by 2g plus Z1, that is equal to P2 by gamma plus alpha V2 square by 2g plus Z2. So, we have to utilize this correction factor, and finally the equation become P1 by gamma plus alpha V1 square by 2g plus Z1 is equal to P2 by gamma plus alpha V2 square by 2g plus Z2. So, to get a correct value, say this energy kinetic energy correction factor to be used, to be multiplied with respect to the velocity head V1 square by 2g or V2 square by 2g when we use the Bernoulli's equation or the energy equation as shown in this slide. So, finally, to conclude this say the Bernoulli's equation or the energy equation. So, as I mentioned earlier, say we have to see the various losses, whether any say the various energy levels are added or taken out, or the external work done, all these things to be considered while we solve real or practical field problems. So, the general equation for conservation of energy for incompressible fluid between two sections we can write as P1 by gamma plus alpha V1 square by 2g plus Z1 plus QW plus HE is equal to P2 by gamma plus alpha V2 square by 2g plus Z2 plus E2 minus E1, where this QW is, if the heat is also heat added per unit weight of fluid, so that effects is considered, and E1 and E2 are the internal energies which if it is there where the flow which you are considering, and HE is the external work done. So, this is the final form of the energy equation, even though we have seen the symbol form of the Bernoulli's equation, but when we solve practical problems, we have to see whether what are the any work added or energy is added, or any the losses of energy due to various aspects, so like due to internal energy aspects, any heat added, all these things we have to consider, and the final form of the equation for when we consider the conservation of energy is as shown here. So, now where E2 minus E1 minus QW can be written as reversible plus irreversible head, and irreversible head is we can write it is as head loss, irreversible head is the head loss, and it is the energy loss per unit weight of fluid due to friction and other causes. So, for incompressible fluid we can write total head at 1 plus head added due to machine like pumps or turbine, and then minus head loss equal to total head. So, finally, the equation, the energy equation can be written as H1 plus He minus HL is equal to H2, and if you want to find the work done over a fluid, power input into fluid is equal to gamma Q Hm in watts, where gamma is the unit weight of fluid in Newton per meter cube, Q is discharge in meter cube per second, and Hm is the head added to flow in meter. So, this is the general form of the energy equation which is used to solve many of the practical flow problems. So, this we have now seen various application of the Bernoulli's equation, and then we have seen the general energy equation, and then we later will be discussing various limitations of the Bernoulli's equation, and then we will solve some of the example problems related to Bernoulli's equation.